Welcome. In this series of videos, we'll explore complex numbers. Start with some definitions. Definition, there I'll abbreviate that. J is the square root of -1. Complex numbers were invented to be able to take square roots of negative numbers. This simply means that if I square J, I get -1. I'll note that in the math world and in some other subjects, they use I for the square root of -1. Engineers tend to use J, reserving I for other things. Complex numbers are numbers of the form A plus J times B, where A and B are real numbers. Let's do some examples, e.g., I'll use the letter Z to stand for a complex number. Z equals 2 plus 3J. Or here's another example, Z equals 4J. Or another example, Z equals 3, which I'll point out is exactly the same as 3 plus 0 times J. We'll call this simply a complex number. When there's no real piece, it's all something times J. We'll call it pure imaginary. There's nothing imaginary about this number, but that's a terminology left over from the 19th century. When the coefficient of J is 0, all you have is a real number, so we'll note that is a real number. One more bit of notation. I'll use a boldface C. When I handwrite that, I'll make a boldface C like this to be the set of all complex numbers. That'll turn out to be a useful little bit of notation. Let me point one thing out about the way we use J. J is just a number, so I can write 3 times J or J times 3. They mean the same thing. Often, when I have a symbol, I'll put the J before the symbol, especially if it's complicated, like cosine of t. If I have just a number, I'll usually put the J after. But again, it doesn't matter which I do. Since we're just getting started with complex numbers, we'll need to define a few more things. So if I have a number Z equals A plus JB, then I'll call A the real part. And I'll denote it like this, real part of Z. That's the real part. And I'll call B the imaginary part of Z. That's the imaginary part. Point out one thing. B is a real number. You don't include the J when you talk about the imaginary part. Let's just do some quick examples. If I have Z equals 2 plus 3J, then the real part of Z is 2, and the imaginary part of Z is 3. If I have Z equals a pure imaginary number, 4J, then the real part of Z is 0, and the imaginary part of Z is 4. If I have Z as pure real, then the real part of Z is 2, and the imaginary part of Z is 0. So a real number has imaginary part 0, and a pure imaginary number has real part 0. Now let's practice some arithmetic. Arithmetic is easy with complex numbers. All we need to remember is that the square of J is -1. So let's start with some addition. If I take 2 plus 3J and I add it to 4 plus 5J, I simply add like terms. So 2 plus 4 is 6, and 3J plus 5J is 8J. Subtraction is exactly the same. except I subtract like terms. So if I take this, 2 plus 3, that's a j in there. 2 plus 3j minus 4 plus 5j. 2 minus 4 is minus 2. 3j minus 5j is minus 2j. Multiplication is a little more effort, but it's still easy. If I say take 2 plus 3j and I multiply it by 4 plus 5j, I have to use the distributive law. You might have used something called FOIL in high school. We'll do things in a slightly different order from FOIL. I like to get all the real parts first. So I take my 2 times 4 and I get 8. And then I take 3j times 5j. That's 15j squared. J squared is minus 1, so I have minus 15. Those are the real parts. For the imaginary parts, I have 2 times 5j. That's 10j. And I have 3 times 3j times 4, which is 12j. So what I have here is minus 7 plus 22j. Products like this, you can usually do the arithmetic in your head and simply write down the final answer. Let's do a couple more multiplications. Let's just take j times 2 plus 3j. Again, going for the real piece, I have j times 3j, and I get minus 3. And then the imaginary part is j times 2, so I get plus 2j. One last common thing, if I take 2 plus 3j and I multiply it by 2 minus 3j, I get the following. 2 times 2 is 4. 3j times minus 3j is minus 9 times j squared. Minus minus 9 is plus 9. Now the imaginary terms will cancel. I have 3j times 2 is 6j, and I have 2 times minus 3j is minus 6j, so I have 0j, which is a net answer of 13. The last arithmetic operation is division. Let's do an example. How about 4 plus 5j divided by 2 minus 3j? The issue here is that we have this complex number in the denominator, and we like to write our complex numbers in the form a plus jb. But we've seen how to get rid of the complex number in the denominator. We multiply the top and bottom by 2 plus 3j. In our previous example, we saw that the product in the denominator is now a real number, 13. To remind you, we had 2 times 2 minus 3j times 3j, which was 13, and then the imaginary parts canceled. We've actually done the top also, so I'll just write it out. We have minus 7 plus, that's 10j, and 12j was 22j. So if I want to write it in my official form, I can write minus 7/13 plus 22/13 times j. That's division. I'll point out when we learn polar form for complex numbers, multiplication and division will become more efficient. The business where we take 2 minus 3j and multiply it by 2 plus 3j and get a real number 13 is so common that we have some notation to facilitate it. If I have z equals a plus jb, then its complex conjugate, z bar, is a minus jb. I change the sign on the imaginary part. I will call this the conjugate of z, or sometimes I'll just say z conjugate, or standard terminology is just to say z bar. The bar indicates the bar over the z. That's the notation for conjugation. Let's record the general formula. If I take z times z bar, I have a plus jb times a minus jb. And for the real parts, I have a squared minus j squared b squared, which is a squared plus b squared. And the imaginary parts cancel. A times minus jb and jb times a add to 0. So I get this real number. When we talk about geometry, we'll call this a squared plus b squared the length of z, and we'll denote it like this. It'll be the length of z squared. Should remind you of the Pythagorean theorem.